水車ご両連結をいたします。点検作業のため単独少々となっています。
乗り降りの際にはボタンを押してください。ドアを閉める際には後ろのお客様にご注意ください。
So Chris studied at Yale University. He earned his PhD at some other school in California, not called Stanford. I think Berkeley, that was it. He was at Berkeley. His work on super collider physics and the Higgs boson has been recognized with one of the highest prizes in the American Physical Society, the Sackharov Prize. But I would say what sets him apart from most of his colleagues is not his intellectual prowess, but more importantly, his ability to communicate his passion and his sincere belief that science and physics and particle physics can help reveal the deepest secrets of our universe. So without further ado, let me introduce Dr. Christopher Quigg. Thank you. Sir.
Thank you for coming tonight. It's a great pleasure to be with this audience. You know, all of us think of ourselves as explorers, and explorers need support, of course, financial support, but even more important, being able to come home from our voyages and share our discoveries with people. And we've had the pleasure over many years of doing that with this audience in the Fermilab community. So I thank you for being part of that. It makes our work meaningful. So 50 years ago, this 6,800 site on which we find 6,800 acre site on which we find ourselves looked like this. There were the 400 residents of the planned community of Weston on the east side of the laboratory. Many farm families who had settled here and tilled the soil, the Illinois soil, for many years. And it's very different now. In the space of a few short years, it became an international destination for physicists, welcoming scientists from all over the world and producing results that are valued by people all over the world. It's also named, as you've just heard, for Enrico Fermi, the Italian-American physicist, who was revered by all of us. He died in 1954, so he never got to see Fermilab, nor did we benefit directly from his input. But he was someone that we call the last universal physicist. He was a master of both theoretical physics and experimental physics. And this is something, he knew all the subjects of physics and was able to communicate and teach them. So he's been one of my personal heroes, and it is wonderful for me, and I think for my colleagues, to be at a laboratory that bears his name. The founders of our laboratory, Bob Wilson and others, wanted this to be a quintessentially American laboratory open to the world at large. And one of their first acts was to honor the legacy of what had been here before. So you see on the east side of the laboratory in sock circle, a number of the original farmhouses. Several of them are gathered together here in the building that we call Aspen East, which has served as a dormitory for many years. The little houses in the village of Weston have been used as dormitories, residences.
elliptic curves of complex multiplication. So recall that that an elliptic curve has complex multiplication. I think this has already been spoken about, of course, which in the elliptic curve case simply means that the endomorphism ring of the elliptic curve properly contains the integers. And so one sort of natural question that we could ask is, what do, in this parameter space, what do the J invariants of complex multiplication points look like? Okay? And in particular, we might be interested in the geometry of these things. Well, if you're talking about Zariski geometry, this is a one-parameter family, and so the only question you can ask is about whether this collection of points is finite or infinite. Right? So, a few facts for comparison later. Maybe can you come? Is it possible? Well, okay, anyway. So a few facts for later. So first of all, there's this infinitely many CMJ invariants. Okay. A second fact, which is a theorem due to Schneider, is that an element of the upper half plane corresponds to a curve with complex multiplication if and only if both tau and its image under the J function are algebraic. Okay? And additionally, thank you. Totally falling here. Sorry. require that 2 points, tau and tau prime, on a curve are simultaneously quadratic imaginaries, no matter which quadratic imaginary field we're taking here. Well, the easiest way to do that is to just require that, say, for example, tau prime is an integer multiple of tau. Okay? So these descend under J cross J to the zero loci of modular polynomials. And so this will give you, for each positive integer n, a collection of a particular curve which contains infinitely many special points. Okay. So in some sense, both of these are obvious examples once you know something about the J function, and then of course the phi variable is obvious to everyone. Okay. So the conjecture, which is a theorem, which as I'm going to state it is due to Andre, but generalized to n tuples. So instead of just 2 tuples, by Pilon, although of course you have to write the statement differently in that setting. But the 2 tuple case is due to Andre is the following statement, that the only curve that can contain an infinite set of CM points, or special points, are exactly the ones that you can obviously think of. Okay? So type A and B, let's be a little more precise here. So C is irreducible. Plane curve contains a Zariski-Dense subset special points if and only if C is of type A or B. Okay. And so I wanted to go through all this, although I know it's reviewed for many of you, because I want to point out that when I move to the dynamical setting, essentially all of these things will have analogies. And so I don't want to spend a lot of time on the details of how this is proved, but I do want to make a remark that the key point is that you use this J map, J cross J, to suppose you have a curve that does have infinitely many special points that is not of type A or B. Then you can construct an object that has properties of both a transcendental thing, in the sense that it doesn't have too many points of defined over a number field of bounded degree, but then also has algebraic properties in that it has too many points that are defined over a number field of bounded degree. And so this play of algebraic versus transcendental is sort of crucial to the proof of this theorem, and it will be in the dynamical setting as well. So, again, it's a bit easier in this situation, although I will, if there's time, talk about the general dynamical Andre-Orth conjecture. It's a bit easier to state or predict a conjecture for the dynamical setting in this basic kind of case of a particular family. So, what might I mean by this? So, first of all, the dynamical setting that I'm considering is the following. So let, say, f of z be a rational map, by which I just mean a quotient of polynomials. So viewed as a map of the Riemann sphere, or a morphism of P1. Over the complex numbers. Okay, so this is the basic object of study. To make things interesting, so when I say I'm interested in dynamical behavior, what I mean is that I'm interested in behavior under iteration by a map like this. Now, that behavior is not so interesting at all if the degree of this thing is 1, if we take an automorphism. So we're going to restrict our attention to degree of f being at least 2. Okay. So before I can talk about what the right kind of analog of the Andre-Orth conjecture might be for moduli spaces of these kinds of things, I need to give some definitions that are basic to dynamics. So, definitions. So the main thing we're interested in here, given a particular rational map, is if we take a point in the Riemann sphere here, and we start iterating that point, we obtain a sequence known as the orbit, or the forward orbit, choose at least 2. Now, if we look at the points on the Riemann sphere and ask what happens under iteration by this map, well, the nth iterate of this map actually has a closed form, right? So if we start taking powers by d here, the nth iterate of this map will simply take the d to the nth power of a point z. So what is happening here